Hello everyone, I'm Rishikesh Kamalapurkar from Oklahoma State University and thank you for being here. Unfortunately, we could not make it to Hong Kong for this conference and our proxy presenter also had to cancel their travel plans at the last minute, so we've opted to make a video presentation and I thank you very much for your patience. The talk today is about an online inverse reinforcement learning method for nonlinear systems, and this is work that I've done with graduate students Ryan Self and Mike Horan at Oklahoma State University. We'll start today with an introduction to the inverse reinforcement learning problem, then we'll present a dynamic programming based solution for the problem, then we'll present a system identification method that will allow us to solve this inverse reinforcement learning problem online, and then we'll present stability analysis and simulation results. The problem is formulated as follows. We have an agent with some nonlinear dynamics x dot equals f of xu. The dynamics we're assuming can be separated into a known nominal part f naught and an uncertain part g. We're also assuming that this agent is implementing a feedback policy that minimizes a performance index. The performance index is an infinite horizon integral of a cost function. The cost function is comprised of a state penalty q and a quadratic control penalty u transposed ru, where R is a positive definite matrix and Q is a positive definite function. The objective of inverse reinforcement learning then is to estimate the cost function, which in this case is the function Q and the matrix R, using the measurements of the state X and the control U. The idea or the motivation behind this inverse reinforcement learning problem is the idea that the most succinct representation of a behavior or of an entity or a task that an entity is performing is its utility function. So by estimating or by calculating the utility function, we can then hopefully reproduce the task that they were doing using a similar dynamics or even a completely different dynamic system. The objective of inverse reinforcement learning then is to recover this cost function by observing an agent perform a task. Now, the inverse reinforcement learning problem is inherently ill-posed. It has multiple possible solutions, including trivial ones, and maximum margin, feature expectation matching, and maximum entropy methods have been proposed or developed in past to help distinguish between these multiple solutions. Nonlinear IRL has also been implemented using deep neural networks and Gaussian processes to approximate the value function and the cost function. But most of these methods are offline and they require a large number of demonstrations to back out or to calculate the cost function of the agent under observation. An online inverse optimal control method was recently presented that uses inverse optimal control techniques to find a cost function for an infinite horizon problem for linear systems using exact model knowledge. And we presented preliminary online inverse reinforcement learning results for linear systems that do not require exact model knowledge in the 2018 American Control Conference, and this paper is an extension of that technique for nonlinear systems. So, to solve this problem, let's assume that R is a diagonal matrix and the function Q can be represented using a neural network as given in the second bullet there with some function approximation error epsilon sub Q. Now, if X and U if X and U are the optimal state trajectory under the optimal controller, so the measurements X and U are coming from optimal state trajectory and optimal controller, then they satisfy the Hamilton-Jacobi-Bellman equation, which is given in 4, and the controller, which is an optimal feedback controller, is related to the state by the equation in 5. Now in 4 and 5, H is the Hamiltonian, which is defined as P transpose F plus this function Q of X plus U transpose RU, and V star is the optimal value function, or the optimal cost to go of this infinite horizon optimal control problem. U star is the optimal feedback controller, and nabla sub x denotes the gradient with respect to x of this optimal value function V star. Now, we're going to use 4 and 5 to solve this inverse reinforcement learning problem, but the problem with that is that 4 and 5 involve the optimal value function, which is also unknown. So we're going to represent the optimal value function using another neural network as W sub V star transpose sigma sub V plus epsilon sub V, where epsilon sub V is a function approximation error which is bounded on a compact set. Sigma sub V are basis functions, and W sub V star are ideal weights. Now, if we use the estimates W sub V hat, W sub Q hat, and W sub R hat, instead of the ideal weight W sub V star, W sub Q star, and W sub R star, where W sub R star is just a vector which is made of the diagonal elements in this unknown matrix R that we're trying to find out, we get the expression for the inverse Bellman error, which is given by delta primed, where this quantity y hat is just the dynamics f naught plus g hat of xu theta hat. Now g hat here is an estimate of the uncertain part of the dynamics, which was g. So what we're assuming is that g can be parameterized using some unknown parameters theta, and g hat of xu theta hat is an estimate of g, where we substitute the estimates theta hat for the unknown parameters theta, and that will be made explicit in a minute. And rearranging, we get the expression in 6, where this delta primed, which we're going to call the inverse Bellman error, is just some weights multiplied by some basis functions. The key point here is that these basis functions depend on theta hat, which is our estimate of the uncertain part of the system dynamics. Let's get to the uncertain part of the system dynamics and talk about system identification. As I said, this uncertain part G is assumed to be parameterized as theta transpose sigma, and we haven't included a function approximation error, but it can be included in here without too much change. We've just done this for simplicity. Then the dynamics can be expressed as equation 7 there. Integrating equation 7 over some time interval t minus tau 1 to t for some constant tau 1, some positive constant tau 1, we get the expression in 8. And the expression in 8 can be rearranged to form an affine system, P equals F plus theta transpose G. Now, this affine system is what we're going to utilize to solve for the parameters theta in the system dynamics. What we do is we use a data-driven method, and the data-driven method, what we do is that we record the values of P, F, and G at various different time instances into a history stack. So a history stack, curly H, is just a set of ordered pairs P, F, and G, such that P is F plus theta transpose G. With this, we can develop an adaptive parameter estimate update law using a recursive least squares like formulation, which is given here in 10. And we've done this so that the dynamics of the parameter estimation error can be expressed using a simple linear time varying system, where the script G here is just a summation of G transposed. Now, motivated by the fact that the rate of decay of this theta tilde depends on the minimum singular value of this matrix script G, what we do is when we get a new measurement which is comprised of a value of P, F, and theta, P, F, and G, sorry, we add that new measurement to our data storage only if it increases the singular value of this matrix script G. If it does not, then we just discard that measurement. So we use a singular value maximization algorithm for data storage. Now it can be shown using Lyapunov methods that as long as the history stack is full rank, which just means that the script G matrix has a minimum singular value that is uniformly positive. If that happens, then we can show that the parameter estimation error theta tilde decays exponentially to 0. Now using that, we can carry on with our inverse reinforcement learning. We do something very similar. We record values of x, u, and theta to give to get the expression in 14, which is delta primed equals sigma primed w hat primed. Now this delta primed is just values of the inverse Bellman error, which was little delta, stacked in a vector. And similarly, this sigma hat primed is just the values of little sigma primed also stacked into a vector. So 14 is just a multiple measurement vectorized version of equation 6 over here. Okay. All right. Now we use our Hamilton-Jacobi-Bellman equation. Now if x and u are optimal and if the weights theta hats and w hat are accurate, then the HJB equation would be satisfied, which means the inverse Bellman error would be 0. So in a sense, what we're doing here is given x, u, and theta hat, we're trying to find w hat so that sigma hat prime times w hat prime is equal to 0. Now you'll immediately see that that is a linear homogeneous system that has multiple solutions. Any positive multiple, actually any multiple of a solution is also a solution. So there is an inherent ambiguity in the way this problem is formulated. To get around that ambiguity, in this paper, what we're going to do is we're going to assume that the first element or the first diagonal element of this matrix R in the cost function is known, and we're typically going to assume that it's just 1. Now that assumption is without loss of generality, because that first element, changing that would just simply scale the cost function, and just scaling a cost function in an optimal control problem does not change the optimal solution. So without loss of generality, we assume first element of w hat R is known, and then we separate out the terms corresponding to the first element of wr hat from equation 14 to get equation 15, which is given by which is basically sigma u1 equals sigma hat w hat minus delta prime. Now similarly as before, we're looking for a solution of 15 so that delta prime is 0. So we want to find values of w hat so that sigma hat w hat is equal to negative sigma u1, and that is a least squares problem whose solution is given by this expression in 16 here, just using the pseudo inverse. Now this works, but the problem with this is that the inverse Bellman error delta, which here is just concatenated into this this vector capital delta prime, and more importantly, the matrix sigma hat, which appears in this solution down here, they both depend on theta hat. And theta hat, if you remember, was our estimate of the uncertain part, or the parameters in the uncertain part of the system dynamics. Now, if the estimates theta hat are wrong, which they often are in the transients because we're estimating theta hat using an adaptive update law, then the estimates W hat are going to be inaccurate. So what we're going to have to do is we're going to have to find some way to fix these estimates W hat once we get more accurate estimates theta hat. To do that, we're just going to use the simple way to do it is to use the fact that theta tilde is converging exponentially to 0, which means that newer estimates are better estimates. So periodically, with some preset period, we re-record or we empty the matrix sigma hat, we re-record all of the data, we repopulate the matrix sigma hat, and then we recalculate W hat using this expression in 16. Sigma hat and sigma u1 both we have to purge and repopulate, but we can do that, or we can do something more intelligent, inspired by this the way this integral concurrent learning works. We can come up with a metric eta which kind of captures how accurate these estimates theta hat are, and then once that metric reaches some predefined threshold, then we can recalculate W hat. So we can do it in an event-driven manner, or we can do it in a time event-triggered manner or a time-triggered manner. In the simulation here, we're doing it in a time-triggered manner, but we can also do it using this event trigger where the events are triggered based on this metric eta. The nonlinear system we've selected for simulations is given in 18, where f1, f2, and f3 are the three unknown parameters, and their exact values are given on the slide. The performance index that the agent is trying to minimize is just an integral of x2 squared plus u squared, which results in the ideal cost function weight vector being a vector of 0 and 1, and r being equal to 1, and then q of x, which is the state penalty function, is simply 0 times x1 squared plus 1 times x2 squared. We selected this problem because the optimal controller and the optimal value function for this problem is analytically known. The optimal controller is just u star of x equals negative 3x2, and the optimal value function is given down here with the ideal value function weights being pi over 2, 1, and 1. Since we know the ideal weights in the value function and the cost function, and the dynamics, we can compare the estimates of theta hat and the estimates of w sub q and w sub r and w sub v that come out of our method with their ideal values. When we do that, we get the following plots, and in the plot here on the left-hand side, you can see that the parameter estimation error theta tilde is converging to 0 as expected. And then on the right-hand side, we have the 5 weights, or the 5 unknown weights, 3 in the value function and 2 in the cost function. Remember, we're assuming that one element in the control weighting matrix R is known. Since R here is a scalar, we're assuming that R is known in its entirety. So any unknowns in the control penalty do not appear on this plot because there are no unknowns in the control penalty. And we can see that the estimation errors corresponding to the unknown constants in the value function and the cost function are also decaying to 0. Thank you for your attention, and if you have any questions, we will be happy to answer questions over email. Please email the questions to us at rself, rself, at okstate.edu. Thank you very much.